This video is the fifth lesson for Chapter 7 for AP Calculus. And we're going to be doing some things called volumes of rotation today, and we'll do them next day as well. Just so you know what a volume of rotation is, it's all about creating a three-dimensional shape that has a cylindrical symmetry to it. So it's like you're working on a wood lathe and you've got some sort of profile function or curve that you're following, and then it turns that as it rotates it into a three-dimensional shape. And it's probably good to kind of be aware of just where we're going to be going over the next two lessons. It turns out there are actually sort of 4 different scenarios that you want to be kind of comfortable with. And I think it's probably helpful to kind of look ahead and see what those 4 tasks are that as a student you should be ready to accomplish. Today we're going to start off looking at some things just called coins, and near the end of the lesson we'll actually be doing coins with a lift, and I'll show you what I mean when we get to the last example by what a lift actually is. And then next lesson we're going to take a look at something called washers, and then we'll also take a look at washers with a lift. And each one of these scenarios looks a little bit different. The algebra, the setup to the integral looks slightly different, and it's always good to know, like, okay, what am I shooting for here? Is this a coin? Is this a coin with a lift? Or washers? And today it's going to entirely be about coins. And what we're going to do is we're going to start off by taking a look at just this nice simple function that's here, nice little straight line, that dark blue line. And we're going to rotate it around kind of like you're working on a lathe. We're going to spin that line around until it becomes a three-dimensional shape. And as it does spin around and it becomes three-dimensional, now all of a sudden it's going to turn into, well, that line, that slanted line is going to turn into, that's a pretty bad drawing. I could do better here. That's going to turn into a nice little cone. In fact, it kind of looks like a big carrot, right? This volume of rotation spinning around the x-axis, by the time it's finished, is nothing but a carrot. And we're going to think about slicing it up into some little carrot coins. Now this particular function here, this f of x or y, whatever you want to call it, looks like just a nice straight line. It has a run of 12 and a rise of 4, so it's got a slope of 1/3. It looks like it's just 1/3 x for that dark blue line that's there. And then as it spins around, it's going to create this neat little shape that we can cut up into coins. And we just have to tell the calculus, how do you go and find the volume of one of those coins? And then the calculus will go and figure out exactly how much volume there is for the whole thing. So again, there's this axis of rotation, and this particular axis of rotation is actually nothing but the x-axis. Okay, that's what a simple coin always looks like. We're just going to spin it around the x-axis. So this is our axis of rotation. Yes, it's the x-axis. It's also, if you think about it, just, y equals 0. Right? That's the equation for the x-axis. Each one of these coins is located at a very specific x value, and the thickness of that coin is going to be dx. And our task, just like it's been for the last couple of days, is just going to be to teach the calculus how do you find the amount of volume in that one little element, and then we can get it to just add up all those volumes for us. Now the radius for this little carrot coin here is just going to be the size of that red line. So that red line goes from the function, which I have in blue, down to the x-axis, which is just y equals 0. So really, if I kind of extract that coin here for a minute, let's put it over here for just a second. That coin's got a radius which is nothing more, in this story, nothing more than just f of x, right? Because it's like f of x minus 0. And then the thickness of this coin going this way, that's just going to be dx. Okay, here we go. Let's go and find the volume of this thing. So our plan is to just tell the calculus that we're going to be summing up a whole bunch of little coins, a whole bunch of little dv's. Okay, that's our plan. And so generally, when you go and do these volumes of rotation, you're going to have sum, and you're going to have, and I'm just going to go and find the volume of a little pancake. It's going to be pi times some sort of radius squared. Well, the radius, I'll just stick it in brackets here. The radius is really just going to be the function. It's just f of x. You know, technically it's f of x, which is up here, minus 0, minus the x-axis, which is there. That's the distance between that blue dot and that purple dot. So that's my radius. I do need to square it if I'm going to try to find the area of that circle, and then I have to multiply by the thickness, right, of that little pancake, and that'll be dx. Now, a lot of people, they like to actually extract the pi out, just kind of pull it out. Constants can always come out of an integral sign, and a nicer, quicker way of writing that function being squared would probably just be to write it like that. And then our dx for the thickness. There will be some starting and stopping value for the x's, right, for where it begins and where it ends. And that's how we're going to go and find this volume of rotation. Now let's try it out with this specific cone that's up there. It's just actually a straight slanted line, and when you spin it around and you stand it up on end, yeah, it'll look like a nice little cone like that. So that cone up there, if you tip it so it can sit on its base, would actually have a height of 12 and a radius of 4, that specific one there. And so this is what it would look like to actually go and find the volume for that cone if you want to do it as a volume of rotation. So we're going to sum up, and I'm just going to think just pi r squared times the thickness, right? Just let the calculus do the work for you. So pi, and then the radius of those coins, it would actually just be the height of that function, so 1/3 x, and that gets squared. It's kind of like 1/3 x minus 0, right? 0 would be the x-axis, and dx. Oh, it looks like x's are in charge, so we'll go and take a look back here and figure out where's the first x. Looks like the very first x that we have to begin our coins at is right here at x is equal to 0. And the very last x, the very last coin, is at x is equal to 12. So yeah, I'm just going to say, hey, you got to integrate calculus from 0 to 12. There, the setup's done. That's kind of the big thing of the day, is right there. Now it's just some old news to you, just trying to find an antiderivative. This volume, a lot of people just pull the pi out. They don't worry about it. I would simplify this before you get going here. Maybe I'll leave the pi for one more line. I'm going to have a 1/9 x squared. Haven't done any calculus yet. I'm just getting ready to. We'll go from 0 to 12. Okay, antiderivative. Again, the pi, you can leave it with all the other stuff. There's like a 9 in there. The x squared is going to become an x cubed with a little bodyguard, a little 1/3. And then I'm going to go and evaluate this from 0 to 12. Obviously putting 0 in is pretty easy because you don't get anything there at all. And then putting the 12 in, I like to, if I'm using my calculator, not put the pi in and then just add the pi later. So without the pi, you get a 64, and then the pi goes on there. So we get 64 pi. And so what we've just done is we found the volume, and we never actually used this equation for the volume of a cone, that 1/3 pi r squared h. You know, maybe you saw that in, like, I don't know, math 10 or something like that. We never actually used that at all. We actually just did this from the idea of a volume of rotation. Okay, so now instead of doing that specific cone, let's see if we can create this equation right here, this one from, you know, junior math. Can we find the volume of a cone that just has a height of h and then a radius of, I'll call it just r. And so we're going to see if we can prove that that formula 1/3 pi r squared h is actually correct. So we're going to create a little volume of rotation. It's like we're working on a wood lathe. So I'm going to set up my graph here. I've got my x-axis. The x-axis, that y equals 0 is going to be my axis of rotation. And if I want to make a cone, then all I have to do is just take a slanted line. And if I take that slanted line and spin it around, then as I spin it around the x-axis, around that y equals 0 line, this is going to create a nice cone shape. Okay, it's going to turn it into a 3D shape, something kind of like that. Now I would like to have this particular cone have, when it's done, a radius of capital R, and when it's done, I'd like it to have a height, when you stand the thing up, of capital H. Okay, that'll be its height. So I have to think about that blue, that dark blue line here. What would the function for that be? You know, what's my f of x, or some people might like to call it y? Well, it's got a straight line. It's a slope of rise over run. It would be r on top of h. So these are just some constants, r and h, and then multiplied by x. Okay, here goes. We're just going to ask the calculus to go and find the volume of a little coin and then add all the little coins up. Okay, that'll be the plan. So generally speaking, for volumes of rotation, we're going to have a pi. The radius, if you're just going to rotate around y equals 0, right, if that's your rotation point, then that radius is nothing more than the function. And it is radius squared, so we'll square the function and then dx. All right, we're up. We're going to see if we can prove that equation. So the volume would be an integral. We have to integrate a pi, and now the radius squared. That'll just be the function. So I'm going to put in here r on top of h multiplied by x. That'll get squared, and then dx. So I have pi, a radius squared, and then a thickness. Now I see that the x's are in charge, so I have to think about, you know, where are we going to start integrating? Looks like we start right here at x is equal to 0, and we're going to stop right there. It looks like that would be at x is equal to capital H. So I would have in here 0 out to h. All right, now all we have to do is this antiderivative. I would probably simplify this integrand first. So there's a pi, there's a capital, that's just a constant. It gets squared, this constant gets squared, and then here comes the interesting algebra, x squared dx. So we have to do an antiderivative of that x squared. And then when we're done, we'll evaluate from 0 out to h. Okay, antiderivative for that thing. Well, the pi is going to hang around. These, just some constants, they're going to hang around, and now the antiderivative. It'll be an x cubed with a little 1/3 bodyguard. So if you're ever wondering, why is there a 1/3 in a shape like that that goes up to a sharp little tip? The answer is because of the antiderivative of the x squared. And then we'll evaluate from 0 to h. Now those are values for x, okay, so they're going to go in here for x. And when you put the 0 in, obviously that's just going to go away. It's quite nice. And so what do we have when we're done? We'll have a pi. There'll be an r squared on top of an h squared. There's this magical little 1/3 that we were looking for, and then an h cubed. You know, minus 0, right, when you put the 0 in. And you can tidy that up. The h's reduce a little bit, and it's true. Your math teacher wasn't lying to you. We've got a 1/3. There's going to be a pi. There'll be a radius squared for your cone. The h's reduce, and you have just an h when you're done. And so that's awesome. We can sleep well tonight knowing that that equation was actually right. And while we're on a roll here, let's do one more of these little verifications just to make sure that our previous math teachers weren't lying to us. What about trying to do the volume of a sphere? And for a sphere, you only need a radius. So let's say the sphere is of radius r, right? We're going to try to figure out exactly what that volume would be. So we have to draw a picture that's going to create, when you spin it around like a wood lathe, that's going to create a ball, going to create a sphere. And so I think I'm going to have to spin around like a half circle in order to do that. So let's just draw our plan out here. Okay, so I've got my x-axis, my y-axis, and what I'd like to do is do a volume of rotation where I take a half circle, and I'm going to spin it around the x-axis. So if I spin it around that, you know, y equals 0 line, then it's going to turn into a nice little ball. It'll have a symmetric bottom to it as it spins around. I would like this particular sphere, once it's created, to have a radius of r to it. So no matter which way I measure from center, I have to see that, oh yeah, that's always r. And up here, that would be r. And even going back this way, right, it's a nice little ball. It's always got a radius of r wherever you measure it. Okay, I do need to know the equation for this half circle up here. And for circles in general, the equation is x squared plus y squared is equal to radius squared. And I want to solve that for y. So I would have y squared is equal to the radius that I'm looking for squared minus the x squared, and then I can take a square root. So here come your half circles. You could do the plus or the minus version. I'm going to take the plus version. Okay, that upper dark blue half, radius squared minus x squared. So that capital R is just a number. We just don't know what it is yet. Again, I don't really need plus or minus. I'm just going to take the positive version. That upper half will be fine. If I rotate it around like a wood lathe, I can turn that thing into a nice little ball. Okay, here goes. This is just for fun, just to see if we can actually prove the equation is right for the volume of a sphere. So the volume is going to be a sum of some dV's. So we're going to be integrating, just think like pancakes now, right? Think about the little coins that would be in here. And how do you tell the calculus how to find the volume of one of those? Well, it's a little pancake. We're going to have to go pi times the radius of that pancake. Well, that'll just be the function. And that has to be squared. And then the thickness, dx. So I'm just going to take this function and put it in here. Now, where does it begin and where does it end? Well, the whole story, it starts here and it stops there. So we're actually going to be going from negative r to r. I guess you could just go from 0 to r and double your answer because this ball is symmetric right around the origin. But we're going to do the whole thing right from negative r to r. Okay, now here goes. I'm going to go from minus r to r. Yeah, there's a pi. And now the function. Well, the function itself looks a little intimidating because it's got this square root to it. R squared minus x squared. But here's the good news. You're going to take that function, and according to the story, you're going to square it, right? Because you have to go radius squared and then dx. So you're actually going to be squaring a square root. That's kind of nice, right? It's actually just going to turn into a nice little simple honest function. So we've got this integral from minus r to r, pi, and then this will just be this number. That's just a constant, minus x squared. The only variable there is the x, right? We know that because it says dx. Okay, antiderivative. I'm actually going to pull the pi and just kind of leave it out front, just so it doesn't look quite so messy. And now the antiderivative. Antiderivative of just a number, you know, r squared is just a number. That would be r squared times x. And now this one's a little more interesting. We're going to have an x cubed with a little 1/3 bodyguard in there. Okay, and then the evaluations from minus r to r. Those are values that are going to go in for x, right? These are always x values that sit out here. Okay, it's going to get a little messy before it gets better, but then it's actually going to get really nice. So this volume for this sphere, there's a pi sitting way out there. I'll put some big brackets on this. Now let's go and put the capital R in. You're going to have r squared times an r. Okay, well that's like r cubed minus 1/3 times r cubed. Okay, great. That was putting the r in. Now putting the minus r in. Subtract. I'm going to have an r squared times a negative r. Ooh, like a double negative there. And then we're going to have, oh, actually, this will turn into a positive 1/3 r cubed, right? By the time I put the negative in, cube it, and then that minus sign. Okay, so tidy this up here a little bit. What do we have? There's an r cubed minus a 1/3 r cubed, double negative, plus an r cubed, and distributing the minus a 1/3 r cubed. All right, hey, we could just go with common denominator of thirds. That's like 3/3. 3/3. So we've got a 3 minus a 1 plus a 3 minus a 1, and that indeed does get you to 4. So we're going to have exactly as we were hoping. We're going to have 4/3 pi r cubed. So now you know where that formula comes from. If you're ever wondering, why does it look like that? Well, it's actually just a volume of rotation, and you can see that it's got to have that 4/3 to it, and then the r cubed. Okay, so all of those questions that we've been doing so far, they have all been stories where we've been rotating this function, this was a half circle, around the x-axis, around y equals 0. Okay, that was our rotation line. Now we're actually going to do something a little bit more interesting. Now we're going to go and do a lift. Okay, so just so you know what makes this question different, this one is what I would call a lift. We're going to find the volume of rotation formed between x equals 1 and x is equal to 4. Okay, so we've got some starting and some stopping points. We're going to start here and we're going to stop here at 4 because they said so. Got this interesting function there. They're like, oh yeah, try this function out. Okay, this f of x is 4 on top of x plus an x. Okay, kind of a neat function. But here's what's different. Here's what's going to make this thing a lift. Okay, we're going to rotate this thing around y equals 6. So up until this point, we used to say, oh yeah, okay, here's your axis of rotation, right? The x-axis. Well, that was true for the first 3 examples, but not anymore. That's not going to be our axis of rotation. Now we're actually going to go and use this y equals 6 as our axis of rotation. Okay, right up here, y equals 6 is the line, and we're going to barbecue this thing around that line. That's where we're going to spin it. So you have to imagine what that function, that black line there, is going to look like when you start spinning this thing around. And so this point, as it spins around, will go up to here. It's going to look kind of like that. This point where we begin will go up to there. Kind of looks like that. And I think it's going to look kind of like this. It's going to kind of look like a chicken drumstick. But what's neat is that this thing is spinning around this y equals 6 line. That's going to be our axis of rotation. So now we have 2 y's to take a look at, right? We've got this green 4 on top of x plus x, and then that purple line, y equals 6. And when you go to think about teaching the calculus how to find the volume of the little coins, that's actually going to be your radius. Okay, it'll be that big. Or if you wish, in here, right, it's the same thing. So it doesn't really matter whether you go the y equals 6 minus the green function that's there or the other way around, but we'll have to subtract in order to figure out what that radius is. So we have 2 y's, so to speak. It's kind of like there's this, this y2 right here, and then like a y1 right there, and we'll have to subtract them in order to find the radius. Still thinking about it in terms of coins. They're still coins. If I was to slice this little chicken drumstick, I could actually create little chicken coins like that. And I just need to teach the calculus how to find these volumes. So the volume here, still going to think about it as just summing up a whole bunch of little dv's. I'm going to think of it as being a pi times some sort of radius. Just think about it that way. Hey, I got to go find the radius, and it's got to get squared and then multiplied by some thickness. And that thickness is just going to be a dx for us. Okay, so getting this rolling here, we're going to be integrating. There's going to be a pi, and that pi can drift outside the integral sign pretty quick. And now, because of the lift, we're going to have to take one function and minus the other. We're going to have to do like a y2 minus a y1 and then square it. You'll have to subtract before you square. And then the thickness, dx. The order that you're actually subtracting doesn't really matter because you're going to square the answer. Okay, so I'm going to put in here, the order doesn't matter. I've often seen people who always put the rotation axis last, like the y equals 6. They might put that last. But I'm going to write them both down here just so that you can see it's totally okay. So this particular answer here, I'm going to be integrating. They told me the start number is x equals 1 and the stop number is x equals 4. So from 1 to 4. And I'm going to have a pi And now here goes, figuring out my radius. I need to take one function. I'm going to put it in brackets so my order of operations will be right. Plus x. Take away 6. That measurement, as I go one minus the other, that'll figure out a radius. So I could do that. Or if you want, you can integrate from 1 to 4. Yeah, I've got my pi in there. And it would be totally okay if you went 6 minus, as long as you're using some brackets here, 4 on top of x plus x, and then square that radius, dx. Nobody really cares the order there. As long as you're subtracting before you're doing the squaring, then you're going to be finding this volume with a lift. So the final answer, if anybody cares, I know I actually don't really care, but it's 26.5711 if you want to double check it. The key thing is this lift issue, right? We're not just subtracting 0, we're not subtracting the x-axis, but this part here tells me that we've got a lift going on. We've lifted up that axis of rotation. And if you have to do that subtraction of the lift first. If there's no lift, if it's just going to rotate around the x-axis, then you wouldn't have that minus 6 in there. It would just be the function being squared. So you've got coins, where you just use the function squared, and then coins with a lift, where you take that function value and then subtract off that rotation axis. Next day, we're going to take a look at washers. What happens if this chicken drumstick has a big hole in it? But for now, we'll just do coins, or coins that are lifted up and rotated around a line other than the x-axis, which is y equals 0, right? So down here, if you were just rotating around the x-axis, this would be y equals 0, and then you'd be subtracting 0. So that's the end of our lesson here for volumes of rotation with coins.